Hello everyone, welcome to this lecture series in linear algebra. Today we are going to talk about vector spaces and also we are going to talk about what are subspaces or what is a subspace of a vector space, and in particular we are going to define two special subspaces called the column space and the null space. So first let us see what is the definition of a vector space. So a vector space is a non-empty set V of objects which we call vectors on which are defined two operations called addition and multiplication by scalars subject to 10 axioms listed below. Okay, so for a set V uh, to be a vector space, first that it has to be a non-empty set, and then on this set if we define two operations, okay, one is the addition operation and other is the multiplication by scalar operation, and under these definition of these two operations, if the 10 axioms 10 properties are satisfied, then we call that this set V is a vector space. Okay, so here few things are very important, that the set has to be non-empty. Okay, and then we have to define two operations, one is the addition operation, other is the multiplication by scalar operation, and based on how we define these two operations, if the 10 axioms are satisfied with respect to these two operations, then we will call this V to be a vector space. Okay, so the 10 axiom says that uh, based on let we have some vectors in this V. Okay, so for all vectors u, v, w in set V, and for all scalars c and d, the first axiom says that if we take any two vectors of the set, then their sum is also in the set. Okay, so if you have any two vectors u and v in the set V, then the sum u plus v also belongs to the set V, so it is the additive closure. Okay, so you take any two vectors in V, their sum is again inside the set V. Okay, the second property is commutativeness. Okay, so that means that for any two vectors the sum you can calculate in any order. Okay, so u plus v is same as v plus u. Okay, so the commutative property is true. Third property is associativity. Okay, so it says that you add two vectors u plus v and then add a third vector w, or you add the second and third vector v plus w and then add the first vector u, they give the same result. Okay, so associativity. The fourth property is the existence of zero or additive identity. Okay, so there is a zero vector, okay, 0 in the set V, such that u plus 0 is u. Okay, so there is existence of the zero vector. Okay, later we will take an example to show that this zero vector does not mean 0. Okay, it can be something which satisfies this result. Okay, the fifth property is additive inverse, that for each vector u in set V, there is a minus of u in V, such that u plus minus of u is the zero vector. The zero vector in the fourth property is right on the right hand side here. Okay, so for every u there is a minus u, such that u plus minus u is zero vector. Okay, so again this minus of u does not mean that you just add a negative sign to u. It can be any other vector such that this holds. Okay, the sixth property is the multiplicative closure. Okay, so for any vector u in set V, the c times u vector is also in the set. Okay, so the linear combination of u, or the constant time u, simply the scaling of u, is also in the set. The seventh property is the distributive vector addition, that you scale the sum of vectors or you scale the vectors and then add them, it gives the same result. Okay, so you add two vectors and then scale it, or you scale the vectors first and then add, you have the same result. So it's a distributive with respect to vector addition. Similarly, we have a distributive property with respect to scalar addition, that uh, you add two scalars and then scale the vector, or you scale the vector with respect to two scalars and then add those two vectors, it gives the same result. Okay, the ninth property is that c times du is same as cd times u. Okay, so you scale a vector then again scale it, or you multiply the two scalars and then scale the vector, it gives the same result. Okay, so it is associative scalar multiplication. And finally, there is one last property, which is the identity, that 1 times u vector is u vector. Okay, so if all these 10 properties are satisfied with respect to the operation of addition and multiplication by scalar. Okay, so based on how we define these two operations, and if all these properties are satisfied with those two operations, then we say that the set is a vector space. Okay, so clearly in linear algebra we deal with the Rn spaces, and Rn spaces, in the previous lecture we have already seen that they satisfy the property commutativeness, associativeness, uh, additive identity, additive inverse, where zero vector is the 0 0 0 element of Rn, and minus u is simply minus 1 times u in case of Rn spaces. Okay, and all the distributive property, associative and identity are also satisfied by Rn spaces. So if you have to prove Rn spaces to be vector space, you just need to prove that the additive closure and the multiplicative closure, rest of the properties 2 to 5 and 7 to 10 are already satisfied. Okay, so this is our first example. Okay, thus that the space Rn for n greater than equal to 1, that means the R space or R2 space or R3 space and so on, they are all examples of vector spaces, they are all vector spaces. Okay, we are not going to prove this, but we are going to take some more examples where to prove how the definition of vector space can be used, and maybe one or two counter examples. So the second example is that for n greater than equal to 0, the set Pn of polynomials of degree at most n consists of all polynomials of the form Pt is equal to a naught plus a1 t plus a2 t square plus so on plus an t power n. So it's a polynomial of degree at most n, because the t power n with coefficient an can take value 0. That means, okay, at most n means it can be a constant polynomial if a1 to an are 0. It can be a linear if a1 is non-zero and a2 to an are 0, and so on. It can be quadratic if a2 is non-zero and a3 to an coefficients are 0. So it defines the polynomials of degree at most n. Okay, where a naught, a1, a2, so on, an are coefficients and t is variable. So this set is a vector space. Okay, the set Pn, where this set Pn is polynomials of degree at most n. Okay, so it will contain nth degree and less than nth degree polynomials. Okay, so it is a vector space, and one can easily prove that all the 10 properties or axioms are satisfied with respect to uh, normal addition and scalar multiplication. But if I take a set in polynomials, the set of all polynomials of degree exactly n, then it fails to be a vector space. Okay, so degree exactly n means if this is a polynomial, then an is non-zero number. Okay, then it will be a polynomial of degree n. Okay, so if we have a set of all polynomials of degree exactly n, then it fails to be a vector space. The proof is very simple, that if I take two polynomials of degree n and define them as this, that the first polynomial is 1 plus t square plus so on t power n minus 1 plus t power n, so it's a polynomial of degree n. Similarly, if I define another polynomial 1 plus t square plus so on plus t power n minus 1 minus of t power n, okay, so it's again a polynomial of degree n. Then if you add these two polynomials, then the t power n and here minus t power n, it will add up to make this last term as 0. Okay, so the sum p plus q will be a polynomial of degree less than n. Okay, so that do not belong to this set. Okay, so the closure property is not satisfied here. Okay, so p plus q will give this value and is of degree n minus 1. Okay, so the closure property is not satisfied, and this set of degree exactly n of polynomials is not a vector space. Now take one more example, where the example is the singleton vector space, and it says that the set Z which contain only one element Z with vector addition or the addition operation defined that Z plus Z is Z, and scalar multiplication operation we define as C times Z is Z for any scalar C. Okay, then this set capital Z is a vector space. So we will prove that if we consider this singleton element set with these two properties of addition and multiplication, these two operations, then it will satisfy all the 10 axioms that we have defined for a vector space. Okay, so let us prove the 10 axioms, and we will show that this set is a vector space. Okay, so first property says that the additive closure. Okay, so if there are two vectors u and v in this, then u plus v also belongs to this set. Okay, so if we take two vectors u and v, then because there is only one element here, so u should be equal to this element and v should be equal to this element. So u is z and v is z, and because the addition of z plus z is defined to be equal to z, so we get z plus z as z, and because z is a element of capital Z, so it is true that u plus v belongs to the set. Okay, so additive closure is true. The second property is commutativeness. Okay, so if you take two vectors u plus v, we will prove that it is equal to v plus u. Okay, so again u has to be z because there is only one element, v has to be z, and by vector addition property z plus z is given z. Okay, and so we can again write this z as sum of z plus z as backward. Okay, so z can be written as z plus z, and the first z can be written as v and second z can be written as u. Okay, so we can easily say that u plus v is v plus u. The third property is associativity. So again we have start with the left hand side, that u plus v plus w, and again u is a vector of capital Z, but there is only one element, so u has to be z, v has to be z, and w has to be z. Okay, now we have to first solve the bracket, and because z plus z is z, so this quantity is z, and so this plus z. Again we can use the same property, that z plus z is z, or we can use on the second element z backward, that this z can be written as z plus z. Okay, so we can rewrite this as the first element as z and second element is written backward as z plus z, and so first is u and second and third are v and w, so associativity is proved. Okay, the fourth property is the existence of zero okay, and it says that there is a 0 vector 0 in capital Z such that u plus 0 is u. So this is what we have to prove, and since you see that property says that Z plus Z is Z, so if you compare these two, then clearly Z behaves like a 0. Okay, so the Z behaves like 0 here, so the Z itself is the 0 vector, and so this property is also satisfied. The fifth property is the additive inverse, that for every z vector there is a minus z vector such that z plus minus of z is z. Okay, so here for every z there is a z such that z plus z is z. Okay, and because this z is behaving like a 0 vector, so it is like u plus minus u is 0 vector. Okay, so fifth property is also satisfied. The sixth property is the multiplicative closure, that if there is a vector in this set, then c times the vector is also in the set. Okay, so again, if we calculate c times u, where u is a vector of capital Z, but capital Z contains only one element z, so u has to be z, and so we get c times z, and by the scalar multiplication property, c times z is defined to be z, and z is in capital Z. Okay, so z belongs to capital Z, so clearly this property is satisfied, that for every u vector in capital Z, c times u vector is also in capital Z. The seventh property is the distributive vector addition. Okay, and so the left hand side says that the scaling of u plus v. Okay, and we have to prove it to be the scale of u plus scale of v. Okay, so again, u and v are vectors in capital Z, so u has to be z, v has to be z, so it is c times z plus z, and scalar addition says z plus z is z, so it becomes c times z, and the scalar multiplication says that cz is z, so c of z is simply z, and now the addition backwards, we can apply z as z plus z. Okay, and then each z we can apply scalar multiplication backwards, that z can be written as c times z. Okay, so c can be written as c times z, and this c can also be written as c times z. So c times z is our this z is our u vector, and the second z is our v vector, so c u plus c v. Okay, so distributive vector addition is also satisfied. The eighth property is the distributive scalar addition. Okay, that c plus d times u will be cu plus du, so left hand side is c plus d times u, u is again z. Okay, so c plus d times z, and the property says that any scalar times z is z. Okay, so this c plus d is a scalar, so scalar times z is z. Okay, and then this property backwards, z can be written as z plus z, and then again any z can be written as scalar times z. Okay, so we can write the first as cz and the second as d times z, so it is cu plus d times u. The ninth property is the associative scalar multiplication, that c times du is same as cd times u. Okay, so c times du. Okay, so d times u means d times z, because u is z, and d times z, any scalar times z is z. Okay, so d times z is z, so we get c times z, again c times z is z. Okay, by this property, and this property then backward, that z can be written as any scalar times z. Okay, so z can be written as any scalar times z, so we take scalar to be cd, and z is u, so cd times u. Okay, so the ninth property is also satisfied. The 10th property is the identity. Okay, that 1 times the vector is vector. Okay, so 1 times u, and u is z, so 1 times z, by this property any scalar times z is z, so 1 times z is z, and z is nothing but u vector, so 1 time u is u vector. So you can see that all the 10 properties, all the 10 axioms are satisfied clearly for the addition operation and multiple scalar operation which we defined here for this singleton vector. Okay, so this singleton vector is capital Z is a vector space. Okay, so now we take one more example. Okay, we said earlier that the in the fourth property, zero vector need not be the exactly zero element. Okay, so we'll take one example to show you this. Okay, so this is very like crazy vector space where we define a set S to be having two elements x1 x2 such that x1 x2 belongs to complex numbers. Okay, so a set contains uh, elements of two tuples x1 x2 where x1 x2 are complex numbers, and we define the two operations like this, that the vector addition for any vector from S, okay, of the form x1 x2 plus y1 y2. Okay, so adding two vectors u and v is defined as this, that the first element is added to first element plus 1, the second element is added to second element plus 1. Okay, and the scalar multiplication is defined as scalar alpha times x1 x2 as alpha times the first element plus alpha minus 1 and alpha times the second element plus alpha minus 1. Okay, so this is how we define addition and scalar multiplication, and under these two operations this set S is a vector space. Okay, so now we'll prove this again, the 10 axioms which shows that this set will be a vector space. Remember that the elements x1 x2 or y1 y2, they are complex numbers. Okay, so to prove this, again we have to prove the 10 axioms. So first is the closure, additive closure. Okay, so we take any two vectors u and v from the set S. Okay, so if u is a vector in S, then u must be written in this form. Okay, two tuples x1 x2. Okay, and v is a vector in S, then v can also be written in this form. So say v is y1 y2. Okay, where x1 x2 and y1 y2, they are complex numbers. So the rule of vector addition says that if you add two vectors of this form, then this is the result. Okay, the first element plus 1 and second element plus 1. Okay, so if these two are to be added, then first element plus 1 and second element plus 1. So clearly, because x1 y1 x2 y2, they are complex numbers, then x1 plus y1 plus 1 is also a complex number, and x2 plus y2 plus 1 is also a complex number. So if two complex numbers are written in this form, then clearly they belong to set S. Okay, so this belongs to set S. So if u and v are in set S, then their sum is also in set S. Okay, so that's our first property of additive closure. The second property is commutativeness. Okay, so property left hand side is u plus v. Again, u is x1 x2 tuple and v is y1 y2. The addition says that the first element added to first element plus 1 and second element added to second element plus 1. Okay, and then since they are complex numbers, so we can rearrange complex number inside to rewrite this as x1 plus y1 plus 1 as y1 plus x1 plus 1, and x2 plus y2 plus 1 as y2 plus x2 plus 1. Okay, and then we can use this property backward, that the x plus y plus 1, so it goes that the first element here and first element in the second, and second element in the second, first element goes to first and second to second. Okay, so in this it becomes y1 comma y2 1 and plus x1 comma x2. Okay, and this is v, this is u, so commutativeness is satisfied. The third property is associativity. So again we have to start with left hand side, say that u plus v plus w, and so u is x1 x2, v is y1 y2, and w is z1 z2. Okay, so first we have to solve this bracket, that x1 x2 plus y1 y2 by using this addition property. So first element plus first element plus 1, so x1 plus y1 plus 1 plus x2 plus y2 plus 1. Okay, and this plus the w vector z1 z2. So again in these two we have to apply this addition property, that the first element plus first element plus 1, so x1 plus y1 plus 1 plus z1 plus 1 comma x2 plus y2 plus 1 plus z2 plus 1. Okay, so it will be the first element of first plus first element of second plus 1, and first element second element of first plus second element of second plus 1. Okay, Now because x1 y1 z1 they are complex numbers, so we can easily rearrange them inside. Okay, so we can uh, rewrite this as first element. Okay, so x1 x2 plus y1 plus z1 plus 1 y2 plus z2 plus 1. Okay, so by rewriting we can use this property backwards. Okay, and then for this also we can use this property backwards and write it as y1 y2 plus z1 z2. Okay, so again clearly we have u plus v plus w, so associativity is also satisfied. The fourth property is the existence of zero element. Okay, so there exists a zero vector here which is -1 comma -1. Okay, so this belongs to the set S because set S consists of all vectors of having two tuples. Okay, so clearly you can check that u vector plus zero vector, okay, where u belongs to S, so u is of the form x1 x2 and zero vector is -1 -1. So if you add these two by the addition rule says that the first element plus first element plus 1, so x1 minus 1 plus 1, which is x1, and the second element plus second element plus 1, so x2 minus 1 plus 1, which is x2, and x1 x2 is clearly u. So this property is satisfied that u plus 0 is u, where this 0 is -1 -1. Okay, so clearly the zero vector may not be exactly 0, it can be anything. Okay, in this case it is -1 -1. The fifth property says that for every u there exists a minus u such that u plus minus u is 0, where 0 is now defined as -1 -1. Okay, so we'll take that for every u which is of the form x1 x2 there exists a minus u given by this such that u plus minus u satisfies equals to 0 vector, where 0 vector is -1 -1. Okay, so clearly you can see that for u vector minus u is not just minus of adding minus sign, but it is very different. Okay, so for minus u here is minus x1 minus 2 minus x2 minus 2, such that you can see that this property is satisfied that u plus minus u means u is x1 x2 and minus u is this number. Then the addition says that the first element is added to first element plus 1. Okay, so x1 minus x1 minus 2 plus 1, so x1 will cancel out and minus 2 plus 1 is -1. Similarly second element plus second element plus 1, so x2 minus x2 minus 2 plus 1. Okay, so again you get -1, so clearly you get this zero vector. Okay, so fifth property is also satisfied. The sixth property is the multiplicative closure, that scalar times u is in the set. Okay, so scalar times u means u is x1 x2 form, so scalar times this, the definition we have defined that it is scalar times first element plus scalar minus 1. Okay, and comma scalar times second element plus scalar minus 1. Okay, so clearly because x1 is a complex number and alpha is just a scalar, so we can multiply and see that this will be a complex number. Similarly alpha x2 plus alpha minus 1 will be a complex number, so two complex numbers written inside bracket separated by comma, so this must belong to S. Okay, so for every u vector alpha u belongs to S. Okay, seventh property is the distributive vector addition, that alpha times u plus v is alpha u plus alpha v. Okay, so again alpha is a scalar times u is x1 x2 and v is y1 y2. So we first we apply the vector addition rule, which is the first element plus first element plus 1 and comma second element plus second element plus 1. Then when alpha is multiplied to this, then this rule comes that alpha times this is scalar first element alpha minus 1. Okay, so alpha times this first element x1 plus y1 plus 1 plus alpha minus 1. Okay, and the same rule to second, alpha times this whole quantity plus alpha minus 1. Okay, so what we will get is alpha times the first element plus alpha minus 1 and alpha times the second element plus alpha minus 1. Now inside is the complex number, so we can solve this. Okay, and rewrite it as alpha x1 plus alpha minus 1 plus alpha y1 plus alpha minus 1 plus 1. Okay, so adding a minus 1 plus 1 on the left and also adding a plus minus 1 on the right, and writing alpha x2 plus alpha minus 1 plus alpha y2 plus alpha, and adding and subtracting 1. So clearly now we can separate this by using addition rule backwards, because this is the first element alpha x1 plus alpha minus 1 plus the second element alpha y1 plus alpha minus 1 plus 1. Okay, so it's like uh, x plus y plus 1. Okay, similarly here also x plus y plus 1. Okay, so we can use it backwards, that first element comma first element plus second element comma second element. So clearly we'll get this result. Okay, so this gives us alpha x1 plus alpha minus 1 comma alpha x2 plus alpha minus 1 plus the second element alpha y1 plus alpha minus 1 comma with alpha y2 plus alpha minus 1. So this addition rule is applied backwards here. Okay, and then now we can use the scalar multiplication rule backwards. Okay, so if we have this result, then backward is alpha times x1 x2. Okay, and this backwards is alpha times y1 y2. Okay, so clearly first is u vector, second is v vector, so we get alpha u plus alpha v. Okay, so seventh property is also satisfied. The eighth property is distributive scalar addition. So that means alpha plus beta times u is alpha u plus beta u. Okay, so u is of the form x1 comma x2, and we know the scalar rule that any scalar time this is scalar time the first plus scalar minus 1 and comma scalar time x2 plus scalar minus 1. Okay, so alpha plus beta x1 plus scalar alpha plus beta minus 1, and scalar time x2 plus scalar minus 1. So again we can solve the complex number inside. Okay, and rewrite it as alpha x1 plus alpha minus 1 plus beta x1 plus beta, and add subtract 1. Okay, similarly alpha x2 plus alpha minus 1 plus beta x2 plus beta, add and subtract 1. So again we can use this as one element plus second element plus 1, and one element plus second element plus 1, so vector addition operation backwards. Okay, so it immediately gives us this separated form, and then scalar multiplication backwards gives us alpha times x1 x2 plus beta times x1 x2. Okay, so which is alpha u plus beta u. So eighth property is also satisfied. Now ninth property is the associative scalar multiplication, that alpha times beta u is alpha beta times u. So again we start with left hand side, alpha times beta times u is x1 x2. So first use beta times x1 x2, so scalar times first element plus scalar minus 1, scalar times second element plus scalar minus 1, and then again it is a scalar times one element comma second element. Okay, so scalar times first element plus scalar minus 1, and scalar times second element plus scalar minus 1 is again used. Okay, so alpha times element beta x1 plus beta minus 1 plus alpha minus 1. Okay, so that's one rule, comma scalar times the element plus scalar minus 1. Okay, so second, again we can open this complex number inside, and we can rearrange this to write alpha beta times x1 plus alpha beta minus 1. This minus alpha plus alpha cancels out. Similarly alpha beta x2 plus alpha beta minus alpha plus alpha cancels out, and minus 1. Okay, so clearly alpha beta is a scalar times element plus a scalar minus 1, scalar time element plus scalar minus 1. So property can be used backward to write alpha beta times x1 comma x2, and so that is alpha beta times u vector. So ninth property is satisfied. Okay, and finally the 10th property says that the 1 times u, okay, u is x1 x2. Okay, so again we have to use the property that any scalar times x1 x2 is scalar times first element plus scalar minus 1. Okay, here scalar is 1. Okay, so 1 times x1 plus 1 minus 1. Similarly alpha times x2, so 1 times x2 plus alpha minus 1, so plus 1 minus 1. Okay, so it comes out to be x1 x2, which is u. So 10th property is also satisfied. So you can see that all the 10 axioms are satisfied for the set S under the operation of addition and scalar multiplication, which was defined very differently. Okay, and so the set S here, since it is satisfying all the 10 axioms, so it must be a vector space. Okay, so set S is a vector space. So this was about vector spaces. Okay, now we return to Rn spaces, and now we will only work with Rn spaces. And first definition in Rn spaces that we need, or we are going to define, is subspace. Okay, so subspace of V, uh, by definition, a subspace of a vector space V is a subset H of V that has the three properties. Okay, so in fact, so with these three properties, this must also be true that if we are going to prove H to be a subspace of V, then H has to be a subset of V first. Okay, so if you have a subset H of V, then it will become a subspace of V if these three properties are satisfied, that the zero vector of the vector space V is also in the subset. Okay, second, for any two vectors in the set H, the sum u plus v is also in the H, so additive closure is there. Okay, and for each u vector in H and each scalar C, the vector cu is in H, so that means the multiplicative closure is also there. Okay, so one, that the set has to be a subset of the vector space. Second, the zero vector of the vector space must be in the subset, and the additive closure and multiplicative closure must be satisfied for H. If this is true, then we will say that H is a subspace of the vector space V. Okay, so and the first example is that the set consisting of only the zero vector in the vector space V is a subspace of V. Okay, called the zero subspace and written as this. Okay, the set of only one vector, which is a zero vector. Okay, so it clearly satisfies all the three properties. First is that the zero vector is in H. Okay, so clearly this set is consisting of zero vectors, so first is true. And we also saw in singleton set that the zero vector singleton set satisfy these two properties. Okay, so it is a subspace of the vector space. The second example is that the vector space R2 is not a subspace of R3. Okay, in fact, any vector space Rm is not a subspace of Rn when m is not equal to n. Okay, because they are in fact not subsets. Okay, so because R2 is not a subset of R3. Okay, in R2 the elements are of the form like A, B. Okay, only two elements in the vector, but in R3 there are three elements in the vector A, B, C. Okay, so the vectors in R2 do not belong to R3, or the vectors in R3 do not belongs to the R2. Okay, so R2 is not a subset of R3, so even this property is not satisfied. We will not talk about the rest of the properties then. Okay, uh, a plane in R3 not through the origin is not a subspace of R3. Okay, clearly, because the zero vector has to be there. Okay, so because the plane does not contain the zero vector of R3. Okay, so that means if you are given a plane in R3 which is not passing through origin, then that will not be a subspace of R3. Or similarly, if you are given a line which do not pass through origin, then that line will not be a subspace of R3. Okay, or in fact instead of R3 you can say a line in R2 not passing through origin, so it will not be a subspace of R2, and so on similarly. Okay, or take one more example here. Say given two vectors v1 and v2 in vector space V, and let H be the span of v1 v2. Okay, so H is a set which is span of these two vectors. Span of two vectors means the set of all linear combinations of these two vectors. So any vector in H can be written as a linear combination of v1 v2. Then H is a subspace of V. Okay, and we'll prove that all the properties are satisfied. So the first property, or in fact first you must see it is a subset of V, okay, clearly, okay, because the vectors in this are linear combinations of v1 v2 and v1 v2 are in V, okay, so clearly it is a subset of V. Now the three properties says that a zero vector is in H, okay, because zero vector in H, if 0 can be written as a linear combination of v1 v2, and clearly we can always write zero vector as a linear combination by scalar 0 0. Second property is that if you take any two vectors in H, then their sum is also in H, okay, so if I take two vectors u and v in H, that means u and v can be written as linear combination of these. So let u is a linear combination of v1 v2 and v is a linear combination of v1 v2, then we will have to prove that u plus v also belongs to H, okay. So if I now calculate u plus v, then clearly u plus v is sum of this combination and this combination, and then we can combine v1 and v2 terms. S1 plus t1 is another scalar, S2 plus t2 is another scalar, okay. So again u plus v can be written as a linear combination of v1 v2, so u plus v belongs to H. Now third property is that if C is any scalar, then Cu belongs to H, okay. So if we define u as this linear combination of v1 v2, then C times u will be C times this, and so it will be CS1 times v1 plus CS2 times v2. So clearly Cu can be written as a linear combination of v1 v2, so C times u also belongs to the set H. So all the properties are satisfied, okay. So clearly H is a subspace of vector space V. So in general we can extend this to say that if you have v1 v2 so on vp are vectors in the vector space V, then the spanning set of v1 v2 vp is a subspace of V, okay. So that means whenever you will have a spanning set of vectors where vectors are from the vector space, then the spanning set is a subspace of that vector space, okay. And given any subspace H of a vector space V, a spanning or generating set for H is a set V1, V2, Vp in H such that H is equal to span of V1, V2, Vp, okay. Okay, so if H is a subspace of V, then H is a spanning set and it can always be written as span of the vectors, okay. uh, Another example, say let H be the set of all vectors of form this, okay, a minus 3b comma b comma a comma b minus a. So vectors are in R4, okay, there are 4 elements where a and b are arbitrary scalars, that is H can be written as a set such that a b belongs to real numbers. Is H a subspace of R4, okay. So clearly the vectors are in R4, okay, and the only question is whether this is a subspace of R4 or not, okay. So vectors are of R4, so H contains vectors of R4, so clearly H is a subset of R4, okay. And then if we rewrite the vectors, okay, so the vectors are having 4 elements, so we can easily write the first element, second, third and fourth in a vector form, and if we rearrange them or decompose them as scalar times vectors, so we can easily rewrite this as a times 1 0 1 minus 1 plus b times minus 3 1 0 1. Clearly you can see that if you multiply, then is a minus 3b, which is first, 0 plus b, so second, a plus 0, so a, and minus a plus b is b minus a. And so we can write it as a times one vector plus b times second vector, a times v1 plus b times v2. So clearly any vector in H can be written as a linear combination of v1 v2, where v1 is this vector and v2 is this second vector. So that means H can be written as span of v1 v2, okay. And By definition, if you have any spanning set, we just prove that it has to be a subspace. Okay, so H is a subspace of R4. Okay, because spanning sets are always subspaces. Uh, Another example which says that for what value of H will Y vector be in the subspace of R3 spanned by vectors v1, v2, v3 if you are given v1, v2, v3 and this Y vector. Okay, so what is the value of this H such that this Y vector uh, is in the subspace of R3 spanned by these three vectors. Okay, so if you remember that if there is a subspace of R3 spanned by these three vectors, so we can write that subspace H as span of v1, v2, v3, and any vector will be in that subspace. That means, and this vector can be written as equal to uh, or this vector will belong to span, means this vector can be written as a linear combination of these vectors. So if we can write y as a linear combination of c1 v1 plus c2 v2 plus c3 v3 for some value of h, then we say that h belongs to the subspace spanned by these three vectors. Okay, so vector y is in subspace of R3 spanned by these three vectors if y belongs to span of these vectors, or equivalently if y can be written as a linear combination of three vectors. Okay, so if we can write y as a linear combination of these vectors, so clearly it's a vector equation, and if this holds, that means the system or the vector equation is consistent. Okay, and now for many lectures we know how to solve this, how to check whether this is consistent. We use the augmented matrix, reduce it to equivalent form, and from there we can check the consistency. So from here we can write the augmented matrix K, which is AV, where A is the v1, v2, v3 vector and the right hand side y. Okay, so A matrix or the v1, v2, v3 vectors and the right hand side y, okay, as the last column. So clearly v1 is given, v2 is given, v3 is there and y is there, so we can easily rewrite this as a matrix. Now we have to reduce it to equivalent form. So again start with the first row, first element, see this becomes the leading element, so make the elements below it 0 by applying row operations. So we can apply row 2 plus row 1 impact on second row, and row 3 plus 2 times row 1 impact on third row. Okay, so these two operations, no change in row 1, so row 1 remains same. Second and third row will change with row 2 plus row 1 impact on row 2. Okay, so minus 1 plus 1 0, minus 4 plus 5 1, 1 minus 3 minus 2, and 3 minus 4 is minus 1. Okay, similarly third row plus 2 times first row and changes in third row. Okay, so minus 2 plus 2 times is 0, minus 7 plus 2 times 5, so 3, 0 plus 2 times minus 3, so that's minus 6, and h plus 2 times minus 4, so that's h minus 8. Now in the second row, this element at 2 2 position becomes the leading element, so we have to make this element at 3 2 position as 0, so we have to apply row 3 minus 3 times row 2 impact on row 3. Okay, so with this operation this matrix reduces to this. Okay, so 3 minus 3 0, minus 6 minus 3 times this. Okay, so it becomes 0, and h minus 8 minus 3 times this, so plus 3, so h minus 5. Now clearly now it is a equivalent form, and if this element h minus 5 is non-zero element, then this becomes the leading element of the third row, and because this leading element will be then in the last column, so system will be inconsistent. And so for consistency of the system, this element has to be 0. Okay, so when h equals 5, then this last element becomes 0 and system becomes consistent. Okay, so the system will be consistent when h is 5. Okay, so for h is equal to 5, this y will belong to the span of these vectors. Okay, so this was our another example. Now we talk about two special subspaces. Okay, one is the null space and the second is the column space. Okay, so first we'll talk about the null space of a matrix. The null space of an M cross N matrix A, written as null A, is the set of all solutions of the homogeneous equation Ax is equal to 0. Okay, so if you solve Ax is equal to 0 system and calculate all the solutions to this homogeneous system, those solutions belong to the null space A. Okay, or in set notation we can write that the set null A is consist of all the vectors x such that x vectors are in the domain Rn and it satisfies this homogeneous equation. Okay, so all the x vectors which satisfies the homogeneous equation. Okay, and see, if you have a domain and a codomain, and here we are talking about M cross N matrix. So if you remember transformation, then we are talking about transformation from Rn space to Rm space. Okay, so there is a domain Rn and there is a codomain Rm. Okay, transformation is from Rn to Rm, and so all the vectors x for which satisfy the homogeneous equation, that means all the vectors x which under the transformation, okay, maps to 0 vector. So all those vectors in the domain which goes to the 0 vector in the codomain, those vector will belong to null space A. Okay, so null space A is a set of all vectors x in the domain Rn such that the homogeneous equation is satisfied. This means transformation on the domain vectors is equal to 0. Okay, so these vectors or these points are transformed to origin. Okay, and so clearly the vectors in null space A are x vectors and those vectors are coming from Rn and Rn is a vector space. Okay, so null space A will prove that it is a subspace of Rn. Okay, so before that let us take one example, that let A be the matrix given by this 2 by 3 and let U be a vector of R3. Determine if U belongs to the null space of A. Okay, whether this vector belongs to null space of A. So any vector will belong to null space of A if Ax is 0. Okay, so if U vector belongs to null space of A, then that means AU has to be 0 vector. So this is simple, that we can check whether A times U gives the 0 vector or not. Okay, so to test if U satisfy AU, simply compute the A times U. A is given, U is given, simply multiply it, and so clearly you get 0 0 or 0 vector. Okay, so yes, U belongs to the null space of A because AU is equal to 0, the homogeneous system is satisfied. So now this theorem that the null space of an M cross N matrix A is a subspace of Rn. Okay, so as I said that in null space A, the definition says that it contains vectors x such that Ax is 0, homogeneous system is satisfied, and because x vectors are coming from domain, so null space has to be a subspace of the domain. Okay, equivalently the set of all solutions to this of M homogeneous linear equation n unknowns is a subspace of Rn. Okay, so this is same as this because null space contains is a set and it is a set of all solutions to the homogeneous system. It is a set of x vectors such that this holds. Okay, so proof of this that certainly null space A is a subset of Rn because A has n columns. That equivalently means that x is a vector of Rn. Okay, because the number of columns times the x vector, that multiplication has to be true. So null space A is definitely a subset of Rn, and to prove it as a subspace we need to prove three properties. Okay, and the first is that the 0 vector belongs to null space A. For any two vectors in null space A, the sum is also there, and for any vector U, the C times U is also there. Okay, so clearly 0 vector belongs to null space A because homogeneous system is always consistent and 0 vector always satisfies this. Okay, so the 0 vector is in null space A because A times 0 vector is always 0. Okay, homogeneous system is always consistent with trivial solution is always there. Okay, The second property is, so let u and v be two vectors in null space A. Okay, that simply means that u and v satisfies the homogeneous system. That means au is 0 and av is 0, and we have to prove that u plus v belongs to null space A. So let us calculate a times u plus v. Okay, so by linearity, a times u plus v is au plus av, and because au is 0 vector, av is 0 vector, and we can add them to end up 0 vector. So clearly u plus v satisfies the homogeneous system, so u plus v also belongs to null space A. The third property, so take any scalar c and again calculate a times cu. C is a scalar, so it can go outside and we can write c times a times u, and au is 0 vector, so c times 0 vector, any scalar times 0 vector is a 0 vector. So again you can see that cu satisfied the homogeneous equation, and so c times u also belongs to null space A. So all the properties are satisfied, and so null space A is a subspace of Rn. Okay, so this is one important result. Now we take one example, that find a spanning set for the null space of the matrix. Okay, so null space is a set of all x vectors such that ax is equal to 0, homogeneous equation is satisfied. Okay, so if we solve the homogeneous system and calculate the x vectors, then those vectors will belong to null space, and then we can easily see that spanning set. Okay, so a vector x belongs to null space of A if the homogeneous system is satisfied for x. Thus we need to solve the homogeneous equation to find all such vectors. Okay, so and we know how to solve the homogeneous system. We solve the augmented matrix, reduce it to equivalent form. Okay, so write the augmented matrix A0. A is this matrix and 0 is the right hand side this vectors, which is 0 0 0. Reduce it to equivalent form. Okay, so here the leading element has to be at 1 1 position, so just to make it 1, so we can interchange row 1 and row 2 so that further operations are easy. So first row, second row becomes first row and first row becomes second row. Okay, now with this leading element at 1 1 position, we have to make the below element 0, so apply row 2 plus 3 times row 1 impact on row 2, and row 3 minus 2 times row 1 impact on row 3. Okay, so with these two operations we can have these two elements 0 and corresponding the elements will change. Okay, now in the second row this becomes our leading element, so we have to make this 0. So either you can apply row 3 minus 1 by 5 of row 2 impact on row 3, or you can first scale this second row down by dividing it by 5. Okay, and then you can subtract two rows. Okay, so either way you can go. Here we are doing 1 by 5 of row 2 on row 2 to scale this element as 1 2 minus 2. Okay, of the second row, and then we can subtract row 3 minus row 2 to make these elements 0. Okay, particularly this element we have to make 0. Okay, so whatever happens to these, it doesn't matter. Okay, so this element becomes 0, correspondingly we are subtracting, so these are also becoming 0. Okay, so row 3 minus row 2 impact on row 3. Okay, is the next step. Okay, and also to reduce it to equivalent form, we have applied row 1 minus 2 row 2 on row 1. Okay, so with the leading element, bottom and top element are made 0. Okay, because we have to solve the system of equations, so we have to reduce it to reduced row equivalent form. Okay, and clearly now we have reduced it to reduced row equivalent form, so all the 5 properties are satisfied. Okay, you remember them. Leading elements are 1, leading elements are the only non-zero elements, 0 rows are below non-zero rows, and so on. Okay, now clearly you can see how many pivot columns, how many non-pivot columns, and because this is the right hand side. Okay, so we only talk about pivot and non-pivot columns from the A matrix. Okay, so first 5 columns, so first column and third column are the pivot columns, and second, fourth and fifth columns are the non-pivot. Pivot columns linked with the basic variables, so x1 and x3 are basic variables, and non-pivot columns are linked to free variables, so x2 second column, x4 fourth column, and x5 are free variable. Okay, Remember, ax is equal to 0, a is 3 by 5, so x has 5 elements, x1, x2, x3, x4, x5. Okay, so x1 and x3 are basic variables, and x2, x4 and x5 are free variables. So there are two basic variables and three free variables. Okay, so we can now easily write the basic variables x1, x3 means the variable linked to pivot columns, in terms of the free variables which are x2, x4, x5, which are the variable linked to non-pivot columns. So first equation, we can calculate x1, which is the basic variable, in terms of x2, x4, x5. Okay, so 2x2 plus x4 minus 3x5. Similarly, from the second row we can calculate the x3 in terms of x4, x5. Okay, so x3 is minus 2x4 plus 2x5. Okay, so these two must go to the other side. Okay, so sign will change. Now we have two basic variable and three free variable. When we write the solution, then the number of vectors in this solution are equal to the number of free variables. So we are going to get exactly three vectors in the solution. Okay, so number of free variables equals the number of vectors that we are going to get in the solution. Okay, means in the solution there are infinite vectors, but we are going to get three independent vectors. Okay, so the vector equation x such that ax is equal to 0 is, so we can calculate x vector, which is x1, x2, x3, x4, x5 by putting this. Okay, so write x vector as x1, x2, x3, x4, x5, and then because we have calculated x1, x3, the basic variables, we can put x1 value and x3 value here. Okay, and then we can decompose this to write it as x2 times vector plus x4 times plus x5 times, so that this is true. Okay, so means x2 times coefficients of x2, okay, plus x4 times coefficients of x4 from here. Okay, so you can see 1 0 minus 2 1 0. Okay, this plus x5 times coefficients of x5 minus 3 0 2 0 1. Okay, so you see minus 3 0 2 0 1, and clearly you see there are three vectors. Okay, we can write this as x2 v1 plus x4 v2 plus x5 v3. Okay, so we got exactly three independent vectors because there are three non-pivot columns, or there are three free variables. Okay, so this vector x can be written as a linear combination of these three vectors. So now we can write that these three vectors are the spanning vectors for the whole space. Okay, they are linear combination, so x belongs to span of u v w. Okay, and so these three vectors are spanning the null space. Okay, so u v w is spanning set for the null space A. Now we take the second important subspace, which is the column space of a matrix. Okay, the column space of an m cross n matrix A, written as column A, okay, or we call it column space A, is the set of all linear combinations of the columns of A. Okay, so if you are given a matrix A with some columns, then the linear combination of columns, the set generated, will be the column space A. Okay, so if A is a matrix with columns A1, A2, so on An, then column space A is the linear combination of A1, A2, An, or we can simply say that column space A is span of these vectors A1, A2, An. In set notation, that means that column space A will consist of vectors such that those vectors can be written as linear combination of these. Okay, so simply that it will consist of vectors B such that vector B can be written as linear combination of these. That means vector B can be written as A times x for some x in the Rn, in the domain. Okay, so that means the vectors B which are in the column space A are the transformed vectors, so they must belong to the Rm space. Okay, so if you are a m cross n vector, there is a transformation from Rn to Rm. Okay, so vector B in column space A are actually in the codomain. Okay, so we are also going to prove this, that column space A is a subspace of codomain Rm. Okay, result, the column space of an m cross n matrix A is a subspace of Rm. Okay, clearly because it contains vectors B such that this system is consistent for some x in domain. Okay, second, the column space of an m cross n matrix A is all of Rm. Okay, it will be equal to the codomain if and only if the system is consistent for every vector in the codomain. Okay, so this is very clear statement. Third, this notation ax for vectors in column space A. Okay, okay, so B vectors in column space A means simply ax vectors in column space A. So the notation ax for vectors in column space A also shows that column space A is the range of the linear transformation x to ax. Okay, so this is a transformation from Rn space to Rm space. That means x vectors are coming from Rn space, and then under transformation ax vectors are going to Rm space. So clearly this all the vectors are belonging to column space A, so it is also acting as the range of the transformation. Now let us take example here that let there is a matrix of transformation, or there is a simply we say there is a matrix A and there is a vector B. Okay, so clearly there is a 3 by 3 matrix, so transformation is from R3 to R3. Okay, so there is a vector B in R3. Determine if B is in column space of A. Okay, so clearly when will any vector will be in column space A if that vector can be written as a linear combination of columns of A. Okay, so this B will be in column space A if we can write this vector as a linear combination of these three vectors, or simply if A times x is equal to B is consistent for some x. Okay, so the vector B is in column space A if Ax is equal to B is consistent. Okay, so again a system of equation, this time non-homogeneous system of equation is to be solved, and if it is consistent then the vector B belongs to column space A. So again for this system we have to reduce the augmented matrix. So write the augmented matrix as AB, so first three columns of A and then the right hand side B as the last column. Okay, apply the row operations. So again leading element at 1 1, so make the bottom element as 0. So row 2 plus 4 times row 1 impact on row 2, and row 3 plus 3 times row 1 impact on row 3. Okay, so it will immediately reduce these two elements to 0, and correspondingly there will be changing in row 2 and row 3. Okay, no change in row 1. Then in second row you have a leading element at 2 2 position, so we have to make this element 0 at 3 2 position. Okay, so apply third row minus 1 by 3 of second row, so that this becomes 0, impact on third row. Okay, so this element becomes 0, and correspondingly these are also becoming 0. Okay, so third row becomes 0 completely. So clearly the system is consistent. Okay, you can see there are two pivot columns. Last column is not a pivot column. Okay, it does not contain the leading element, so it is a consistent system with two pivot columns, one free variable. Okay, and this is the right hand side. Okay, so the system Ax equal B is consistent, and if it is consistent that means B is in the column space of A. Okay, so we'll just close this topic for today now with the contrast between null space A and column space A for a M cross N matrix A. That means there is a transformation T from Rn space to Rm space. Okay, so that the matrix of transformation A is M cross N. Okay, so we have discussed this in previous lecture. Now we simply see what happens in null space A and column space A. We have already seen this, that null space A is a subspace of Rn domain and column space A is a subspace of codomain. Okay, uh, any vector V will belong to null space A if it satisfies the homogeneous equation. Okay, and any vector will be in column space A if the non-homogeneous equation Ax is equal to V is satisfied for some x. Okay, that means if Ax is equal to V is consistent. Okay, so for any vector in null space A, AV has to be 0. For any vector in column space A, Ax equal to V has to be consistent. Okay, null space A will be the 0 vector if and only if the homogeneous system has only trivial solutions. See, any vector in null space A if homogeneous equation is satisfied. So if null space A will contain only one vector and that is the 0 vector, if and only if this system has only one solution, which is this x is equal to 0 solution, that is only the trivial solution. column space A will be equal to the codomain, okay, if and only if the system Ax is equal to B is consistent for every B in Rn. Okay, so if for every B in Rn Ax equals B is consistent, okay, then every vector B will be in column space A. Okay, so every vector of Rm will be in column space A, means these two are equal. Okay. Uh, Null space A will be a set of only zero vector if and only if the transformation is 1 to 1. Okay. So clearly from this you can see that this is true when it has only a trivial solution. Okay, and we know that a transformation is 1 to 1, then homogeneous system has only trivial solution. So this theorem we have already done, so these two results are clearly true. Column space A equals Rn if and only if the linear transformation x to Ax maps Rn space onto Rm space. Okay, so clearly this is again true because for every B system is consistent, so the transformation is onto. Okay, because onto transformation means that every vector in codomain must be coming from domain, so that means system is always consistent. Okay, so this is simple some contrast between null space A and column space A. Okay, so we close this topic here. Okay, and we'll continue in the next lecture to find a basis and dimension for the vector space. Okay, so till then have a very nice day.